When the asteroid struck the region that today corresponds to the Yucatan Peninsula, it released within seconds an energy that far exceeded all the nuclear bombs ever built by humanity. The rock pierced the atmosphere at hypersonic speed, and upon contact with the shallow ocean and rocks rich in sulfates and hydrocarbons, it vaporized water, sediments, and part of the crust. In the first moments, a shockwave traveled across the continent, knocking down forests, triggering earthquakes, and generating tsunamis that traveled thousands of kilometers into the ocean. Meanwhile, the sky ignited. Incandescent fragments re-entered the atmosphere like a rain of secondary meteors and heated the air over vast regions of the planet. In many places, the surface temperature rose enough for forests to begin burning almost simultaneously. The fire did not start as an isolated point. It spread like a network of massive fires that consumed leaves, trunks, nests, and organic soils. For days, perhaps weeks, enormous expanses of land burned almost without interruption. Animals that survived the first hours of the impact found themselves in a world engulfed in flames. Dinosaurs that were still alive had to flee areas that became open furnaces, and many smaller species sought refuge underground in burrows, caves, or damp cracks. Rivers and lakes acted as the last lines of salvation. There, some aquatic reptiles, amphibians, and fish survived while the terrestrial world was reduced to smoke and embers. The air became dense, irritating, and ash-laden. Breathing required extra effort for organisms already at the limits of their strength. As the fires consumed the available vegetation, the sky began to transform into something even more dangerous. Soot produced by combustion rose into the upper layers of the atmosphere, mixing with impact dust and sulfate aerosols released by the vaporized rocks. This mixture blocked a large part of the sunlight. What had previously been a bright planet, dominated by temperate or warm temperatures, became shrouded under a grey veil. Days darkened, shadows blurred, and the normal cycle of light and darkness was distorted. Current climate models show that this stratospheric cloud could have reduced sunlight to levels insufficient to sustain photosynthesis in many ecosystems. For months, and even years in some regions, plants did not grow as before. Entire forests failed to regenerate, grasslands withered, and soils were covered by a mixture of ash, dust, and decomposing organic matter. For large herbivores, this change meant a death sentence. They required enormous amounts of food, and food disappeared. In the oceans, the story was similar. Phytoplankton, which depended directly on light, suffered a sharp decline. With the collapse of this base of the food chain, the organisms that fed on it began to go extinct or drastically reduce their populations. Large marine reptiles, which were already under pressure from previous changes in sea levels and marine ecosystems, now faced an impoverished, less productive, and more hostile ocean. Many of these giant forms failed to survive the winter that followed the impact. On land, cold and dark days followed one after another. This was not a seasonal winter, but a global phenomenon that completely altered the climate. Temperatures dropped, the seasons became misaligned, and rainfall patterns changed. In some areas, acidic precipitation resulting from sulfur compounds and reactive nitrogen in the atmosphere further degraded soils and affected the few plants able to resist. What had once been a vibrant landscape became a grey scene, dominated by burned trunks, eroded surfaces, and murky puddles. However, even in the midst of this prolonged darkness, life did not stop completely. Many small organisms, such as insects, worms, and other invertebrates, continued feeding on plant and animal remains. In burrows, roots, and hollow trunks, tiny mammals exploited their small size and relatively flexible metabolism to survive on varied diets composed of seeds, insects, and carrion. Crocodilians and other semi-aquatic reptiles spent long hours motionless in murky waters, waiting for a fish, bird, or corpse carried by the current to become their next meal. Current fossil records and geochemical studies indicate that this period of shadow and cooling was not permanent, but it lasted long enough to profoundly reconfigure all ecosystems. Where large bodies and plant-based food chains had once dominated, scenarios emerged in which energy conservation, the ability to hide, and dietary flexibility became decisive advantages. Mass extinction did not only eliminate species, it created new ecological rules. In the longer term, the same processes that had caused darkness began to reverse their effects. Carbon dioxide emitted by massive volcanism and the burning of entire forests remained in the atmosphere much longer than dust and soot. Once the opaque veil dissipated, this additional CO2 contributed to a stronger greenhouse effect. Thus, after the initial cold episode, the planet gradually moved toward warmer conditions again, and even milder ones at high latitudes. This climatic backdrop would be crucial to understanding why, a few million years later, the dense forests and wetlands of the early Paleocene provided the perfect setting for the expansion of crocodilians, mammals, and later, the first primates. Freshwater survivors, why some persisted. When the impact dust began to settle and the fires died out, the Earth did not show an absolute void, but a very clear pattern. Freshwater environments concentrated a large portion of the survivors. While the great terrestrial herbivores disappeared and shallow oceans suffered the collapse of phytoplankton, many rivers, lakes, and swamps continued to function as biological refuges. They were not thriving oases, but they offered something fundamental in a broken world: continuity. Lakes and rivers stored heat and buffered sudden temperature changes. When the atmosphere suddenly cooled due to dust and soot blocking solar radiation, the water slowly released the accumulated heat. For fish, amphibians, and aquatic reptiles, this effect acted as a barrier against climatic extremes. Water also protected against another silent enemy: increased ultraviolet radiation, a product of a disrupted atmosphere. Submerged or partially buried in mud, many organisms avoided direct exposure while the sky remained unstable. Additionally, freshwater systems received a constant influx of detritus: fallen leaves, burned logs, animal carcasses carried by currents. Even if forests were devastated, organic material continued to arrive in the form of debris. Bacteria, fungi, and invertebrates decomposed this matter. Small crustaceans, aquatic insects, and fish fed on it, maintaining a food chain based more on decomposition than on new plant production. In this type of ecological economy, survival did not depend on large green forests, but on the ability to recycle what remained. Crocodilians fit especially well into this scenario. Before the impact, they already occupied rivers, marshes, and tropical coasts. Afterward, those same habitats became survival trenches. These animals endured long periods without food, lowered their metabolism in cold or murky waters, and fed on any available prey: fish, amphibians, birds, floating carrion. When abundance disappeared, their slow life strategy and capacity to wait made the difference. Not only did their physiology favor them, but also their behavior. Crocodilians spent much of their time motionless, semi-submerged, exposed to the sun when it reappeared through the dust haze, and returned to the water when the environment became hostile. Females protected their nests and young, a parental investment that increased the chances that at least some juveniles would reach maturity even in difficult conditions. In a world where many reproductive strategies based on large litters with low survival failed, this additional care provided an advantage. Alongside them, other semi-aquatic reptiles also survived the Cretaceous-Paleogene boundary. Choristodorans, for example, were elongated reptiles resembling semi-aquatic lizards that had lived in rivers and lakes since the Jurassic. Many lineages disappeared, but some persisted into the Paleocene. These animals, similar to small gavials or reptilian otters, shared niches with crocodilians in freshwater zones, fishing and lurking among riparian vegetation. Their survival reinforced the idea that aquatic habitats functioned as corridors of evolutionary continuity. Amphibians, in turn, exhibited another form of resilience. Frogs and salamanders, dependent on water for reproduction and with permeable skin, seemed vulnerable to environmental changes. Yet many species lived in permanent ponds or rivers that did not dry up completely. Their flexible life cycle, small size, and ability to bury themselves in mud or take shelter under stones allowed them to survive the darkest moments. Where a thread of water and some food remained, a frog could continue singing, even if that song no longer had the distant roar of a tyrannosaur as its backdrop. Fish also played a crucial role. In deep lakes and fast-flowing rivers, the lower water layers remained relatively isolated from the worst atmospheric changes. Some species fed on detritus falling from the surface, while others hunted invertebrates and small prey displaced by currents. Eggs and larvae, protected among aquatic plants or buried in gravel, maintained populations despite losses. When the climate began to stabilize and light returned, many river systems already had fish communities ready to expand. Amid this network of aquatic survivors, small mammals found complementary refuges. They were not yet the large herbivores or predators of the later Cenozoic, but creatures the size of mice, shrews, or rats, which built burrows near shorelines, hid among roots and fallen logs, or moved under the cover of riparian vegetation. At night, they emerged to forage for insects, eggs, small invertebrates, and remains of dead animals. During the day, they stayed hidden, reducing the risk of being hunted by reptiles or scavenging birds. The margins between water and land became one of the most important stages of this new world. There, remnants of burned forests, nutrient-carrying currents, and the gradual appearance of new plant shoots mixed together. On these unstable edges, crocodilians, choristodorans, turtles, amphibians, fish, birds, and mammals shared a narrow space, competing and adapting to every small change in the landscape. Abundance no longer depended on vast plains covered with conifers or mature angiosperms, but on the ability to make use of a fallen log, a sandbank, or a deep pond. Meanwhile, open marine environments took longer to recover. The collapse of phytoplankton and many planktonic invertebrates triggered a cascading extinction, especially among animals occupying the upper levels of the food chain. In contrast, smaller freshwater basins with closed nutrient cycles managed to reorganize sooner. This temporal difference allowed freshwater lineages to act as reservoirs of diversity, from which some groups could recolonize other regions when conditions improved. As the Danian progressed, rivers and lakes began to be surrounded by vegetation again. First, ferns and pioneer plants tolerant of poor and disturbed soils proliferated. Later, shrubs and young trees formed incipient forests. Crocodilians, which had endured the worst years of darkness, took advantage of this recovery to expand their presence. Some species adapted to colder waters or higher latitudes than might seem possible today, taking advantage of a planet that, after the initial cooling, once again tended toward warm conditions. The green regrowth, the fern spike, and soil reconstruction. When the fires subsided and the sky began to clear, landscapes that had once been dense forests were transformed into black, bare surfaces. Charred trunks stretched across hills and plains, and layers of ash covered the ancient soils. For a time, rain washed this grey mixture into rivers and lakes, forming murky torrents that eroded slopes and filled valleys. The plant world that had sustained large herbivores no longer existed. What remained was unstable, exposed, and fragile terrain. In this devastated scene, the first protagonists of regrowth were not large trees but ferns. Their spores, light and resilient, had travelled vast distances before the impact and continued to do so afterward. Many became trapped in the soil, others remained in the air or in damp cracks. When conditions improved enough, with a little more light, some stable moisture, and less extreme temperatures, these spores germinated and formed green carpets over the ash. In the fossil record, this phenomenon was marked as a fern spike, a peak in the abundance of fern spores in sediments that occurred immediately after the extinction. Ferns spread like a silent tide. Shoot after shoot, they covered immense clearings, grew along the banks of rivers freshly loaded with sediments, and settled on eroded slopes. Their fine roots and rhizomes helped stabilize loose soil, reduced erosion, and created the first layer of shade over surfaces that had previously been directly exposed to sun and wind. Where ash mixed with burned organic remains, ferns utilized nutrients released by fire and incorporated them into a new biological cycle. Meanwhile, underground fungi and bacteria began reconstructing the invisible networks of life. The remains of trunks, roots, and charred leaves decomposed slowly. Fungi penetrated burned wood, forming filaments that extended among ash particles and rock fragments, transforming dead matter into compounds that new plants could absorb. Earthworms, soil insects, and other small invertebrates burrowed galleries, mixed layers, and accelerated the formation of young soils. The planet not only regained a green mantle, it also rebuilt from scratch the fertile skin that supports nearly all terrestrial ecosystems. Over time, these fern carpets ceased to be the only dominant type of vegetation. In areas where disturbance had been less severe, or where the roots of surviving trees remained alive underground, shrubs and seedlings of angiosperms began to emerge. Small, broadleaf trees sprouted from burned stumps or from seeds protected within buried fruits. At first, they formed isolated patches within the fern fields. Later, these patches grew, merged, and gave rise to young forests. These forests were not exact copies of those that had existed in the late Cretaceous. The selective extinction of many plants, combined with the disappearance of large herbivores, altered the composition of plant communities. Some conifer species recovered, but flowering trees, the angiosperms, gained ground in many environments. Today, it is known that the early Paleocene marked an important step toward angiosperm-dominated forests that characterize much of today's jungles and woodlands. The canopy structure, shade density, and diversity of leaf forms began to resemble the modern world more than the landscape of dinosaurs. In areas near water, recovery was especially rapid. River and lake banks offered constant moisture, soils rich in freshly deposited sediments, and greater protection from subsequent fires. There, fast-growing pioneer plants thrived, shrubs, tall grasses, and trees that tolerated unstable soils. Alongside them grew horsetails, rushes, and other plants well adapted to saturated substrates. These green strips along waterways functioned as biological corridors connecting different habitat fragments. As vegetation recovered, the landscape began to offer three-dimensional shelters again: dense shade on the ground, hollow trunks, low branches, overlapping canopies. Small mammals used this new setting to expand their movements. Some species moved through leaf litter, others climbed thin trunks, and still others combined both strategies. Birds found branches to nest on, cavities to hide their young, and sources of food in the form of insects that multiplied along with the new leaves. The resurrection of green was not only a plant phenomenon, it marked the mass return of ecological opportunities. The soil reconstruction process continued for tens of thousands of years. Each cycle of plant growth and death accumulated more organic matter. Roots penetrated deeper, broke rocks, created pores for water and air. Rain, which initially washed away ash and sediments catastrophically, began to infiltrate more gently into structured soils. Differentiated horizons formed, darker layers rich in humus, intermediate layers with a mix of minerals and organic matter, and denser lower layers. This soil architecture allowed forests to become more stable and complex. While forests consolidated in many regions, other areas remained open for longer periods. Exposed plains, young river terraces, and areas subject to periodic flooding maintained communities of low vegetation, mixtures of ferns, grasses, and shrubs. These open landscapes offered niches different from those in closed forests and over time became ideal terrain for running mammals, medium-sized herbivores, and fast predators. Although most mammals were still small during the Danian, the plant foundation that would support future expansions was already underway. From a modern perspective, the fern spike and subsequent plant diversification function as a kind of geological signature of Earth's resilience. Each time a massive disturbance swept through large areas, pioneer plants such as ferns, hardy grasses, and fast-growing shrubs filled the void. After the KPG extinction, this pattern was visible on a planetary scale. Danian rocks record a transition from layers dominated by fern spores and fire signals to sediments rich in angiosperm pollen and remains of young forests. This green regrowth also altered the local and regional climate. As forests grew, they captured carbon dioxide, moderated surface temperatures, and increased air humidity. Rainfall became more regular in certain areas, water and nutrient cycles stabilized, and the atmosphere regained part of its balance. Although the global greenhouse effect was still influenced by volcanic CO2 and other factors, new plant ecosystems began to act as climate buffers. For crocodilians, choristoderas, turtles, and amphibians that had survived in rivers and swamps, the expansion of vegetation meant more complex banks, shadier waters, and an increasing abundance of prey. For mammals and birds, it meant more fruits, seeds, insects, and small invertebrates. Every fern shoot that held a grain of ash, every root that opened a channel for water, and every young tree that raised a leafy crown contributed step by step to building the stage for the Danian world, a planet that no longer belonged to dinosaurs but to a new generation of colonizers. And this world under reconstruction prepared the ground for the next chapter, shaping the climate, rivers, and young forests that defined Danian Earth. The Danian planet, climate, rivers, young forests, and empty niches. When the Danian began, the planet had already left behind the most brutal phase of darkness and cold. Dust and soot gradually dissipated, and solar radiation once again reached the surface with greater intensity. The climate, which had collapsed immediately after the impact, began a slow recovery. On a scale of millions of years, the Earth was heading toward a new warm greenhouse state, different from the late Cretaceous, but equally distant from what is today considered temperate. Global average temperatures were higher than present, and the differences between the equator and the poles were less extreme. Forests and wetlands extended into latitudes where today cold or arid landscapes dominate. Fossil and sedimentary records show that from the early stages of the Paleocene, ecosystems at mid and high latitudes could support faunas that today we associate almost exclusively with the tropics. Among them, groups of crocodilians occupied regions that would now seem too cold for them, evidence of a more uniformly warm planet. The continents were already in full drift toward their modern positions. North America and Eurasia had separated enough to allow the opening of the North Atlantic. South America remained isolated. Africa was slowly moving north. India was approaching Asia. This configuration generated epicontinental seas, broad coastal platforms, sedimentary basins, and growing mountain chains. Rivers originating from these new elevations transported enormous amounts of sediment toward plains and deltas, creating dynamic floodplain landscapes. These plains, with young soils and alternating layers of sand, silt, and clay, provided the ideal setting for expanding forests, extensive wetlands, and an enormous variety of niches. The Danian climate was not static. There were oscillations, periods of greater humidity, and somewhat drier intervals, but in general terms, an atmosphere richer in carbon dioxide and a stronger greenhouse effect than today prevailed. Precipitation was abundant in many regions, hydrological cycles were intense, and erosion rapidly reshaped landscapes. Rivers meandered, changed courses, opened bends, and cut old channels to create new ones. Every time a river abandoned a channel, it left behind lagoons, oxbow lakes, and small depressions filled with stagnant water, perfect habitats for amphibians, insects, small fish, and aquatic reptiles. Along these river networks, young forests that had emerged after the fern spike occupied the plains and slopes. The canopy had not yet reached the towering height of later mature forests, but it already offered several layers of vegetation. In the understory, ferns, shrubs, and herbaceous plants grew. Above them rose trunks of fast-growing angiosperms. In the upper layers, interlaced branches began to form continuous shade roofs. In some places, conifers persisted, integrated into mixed communities. The result was a plant mosaic where light filtered in patches, soils mixed leaves, fallen branches, and ancient ash, and humidity remained high for much of the year. This mosaic of forests and rivers generated an enormous variety of microhabitats. In clearings opened by landslides or fallen trees, pioneer plants, pollinators, and small herbivores thrived. In more closed and shaded areas, fungi, soil insects, and detritivores kept the organic matter recycling in motion. Riverbanks offered fallen logs, exposed roots, and sandbanks where crocodilians, turtles, and amphibians basked in the sun. In shaded ponds, tadpoles, small fish, and aquatic invertebrates formed locally productive food webs. From an ecological perspective, the world was still full of gaps. The disappearance of large dinosaurs had emptied key positions in the food chains: enormous long-necked herbivores, herds of ornithopods, and large predatory theropods. These niches were not filled immediately. During the Danian, many communities had simpler food webs and lower biomass at higher trophic levels. Large predators were scarce. Most terrestrial vertebrates remained small or medium-sized. In this context, crocodilians established themselves as some of the main large predators of freshwater and coastal zones. Their presence in rivers, lagoons, and deltas placed them in a strategic position. Any animal approaching water to drink, cross, or search for food was exposed to attack. Some marine or nearly marine forms, such as the Dinosaurs, survived the extinction and occupied coastal and estuarine environments, where they hunted fish and other vertebrates. Fossil records of genera such as Hyposaurus show how these reptiles crossed the KPG boundary and persisted in early Paleocene sediments. But the Danian was not only the age of aquatic reptiles. In the understory and among tree roots, mammals began experimenting with life forms that, a few million years later, would explode into spectacular radiations. Today it is known that, already in the early Paleocene, mammalian diversity began to increase. Lineages appeared with teeth more specialized for grinding plants, others with sharp teeth for carnivory, and many intermediates, opportunistic omnivores capable of exploiting almost any resource. Most of these mammals were small, but that did not make them secondary players. Their small size allowed them to hide in burrows, hollow logs, and root cavities. Some moved mainly on the forest floor, sniffing through leaf litter. Others climbed low branches, exploring a newly available vertical dimension. Young forests with thinner trunks and less massive structures offered an ideal environment for these first semi-arboreal life experiments. In this environment, later lineages emerged that increasingly resembled early primates. Birds, for their part, occupied the sky and many forest layers. Some species specialized in hunting flying insects. Others fed on fruits and seeds. Still others acted as scavengers, moving among carcasses abandoned by predators or extreme weather events. In the absence of pterosaurs and large theropod dinosaurs, birds had greater opportunities to diversify in forms and lifestyles. The Danian also showed regional contrasts. In zones near the equator, forests were denser and more persistent, with intense rainfall cycles and few interruptions from cold. At mid-latitudes, seasonal changes were more noticeable, but temperatures were still mild enough to maintain forests and wetlands for almost the entire year. Even near the former polar circles, sediments indicate the presence of tree vegetation and faunas adapted to long periods of light and darkness, but not to icy winters like today. Overall, the Danian planet was a world of recovery and possibilities. Fires had already died down, ashes were beginning to integrate into fertile soils, and the atmosphere was stabilizing into a new, warm equilibrium. Rivers, continuously reconfiguring their courses, created and destroyed habitats at a high rate, favoring dispersal and local speciation. Young forests offered refuges, food sources, and three-dimensional structures that stimulated new strategies for locomotion, feeding, and reproduction. The lords of the rivers, crocodilians, their relatives, and their expansion. When the young Danian forests consolidated around rivers, lagoons, and swamps, the great predators of the New World were no longer dinosaurs or giant marine reptiles, but crocodilians. On a planet where most large terrestrial carnivores had gone extinct, these semi-aquatic reptiles occupied a central position at the top of many food chains. Their history did not begin there, but the Danian offered them their best stage. Long before the impact, crocodilians already inhabited tropical rivers, deltas, and warm coasts. When the asteroid struck and the world darkened, many lineages disappeared along with the dinosaurs, but several groups managed to cross the boundary. In the first millions of years of the Paleocene, those survivors split and diversified. On different continents, fossils of jaws, vertebrae, and dermal plates began to record new forms, adapted to different types of water and prey. It was not a sudden explosion, but a progressive expansion, guided by rivers changing course and forests that were still under reconstruction. On the wide rivers of the floodplains, broad-snouted crocodilians established themselves as opportunistic hunters. These animals hid in murky waters, almost motionless, with only their eyes and nostrils protruding. When a fish, a turtle, a large amphibian, or a thirsty mammal approached the shore, the attack was triggered in a fraction of a second. A tail strike, a thrust from below, a bite that captured the prey and dragged it to the bottom or shook it until bones and muscles broke. The technique has not changed much since then. The strategy observed today in crocodiles and alligators emerged much earlier, and during the Danian was already dominant. Other lineages developed longer, narrower snouts suitable for catching agile fish. In deep waters or quiet channels, these piscivorous crocodilians lurked near schools of fish and lunged with quick head movements. The shape of their skulls, light and elongated, allowed for clean cuts through water, reduced resistance, and increased bite accuracy. In estuaries and coastal areas, some marine or nearly marine relatives took advantage of the mixture of fresh and salt water to hunt prey moving between both environments. There were also forms closer to terrestrial life. In certain Paleocene deposits, crocodilian bones and those of their relatives show longer limbs and robust skulls, with high snouts and sharp teeth adapted for tearing flesh. These animals likely patrolled riverbanks or ventured into nearby forests, hunting mammals and other vertebrates away from the water. Although many of these lineages would reach their peak somewhat later, their roots were planted in the ecosystems that the Danian began to shape. The geographic distribution of crocodilians reflected the warm and relatively uniform climate of the time. As the planet recovered from the initial cooling and the atmosphere retained more heat, large areas of mid-latitudes offered mild conditions year-round. Rivers in regions that are temperate today hosted crocodilian faunas that, in the present, would only be associated with tropical belts. In the deltas and coastal plains of what is now Africa, South America, North America, and Europe, these reptiles multiplied and became symbols of the new wetlands of the early Cenozoic. Their success relied on several biological advantages. First, their slow metabolism allowed them to survive in environments where food was not always abundant. A crocodilian could go long periods without feeding, reducing its activity and expending less energy. In a world where ecosystems were still reorganizing and resources fluctuated, this ability was crucial. Second, their diet was extremely flexible. Fish, amphibians, turtles, birds, small mammals, carrion, and even large invertebrates. Almost anything that fell into the water or came too close to the shore could become food. Reproduction also contributed to their persistence. Females built nests with vegetation, soil, and plant debris, usually in elevated areas near water, and buried their eggs there. The heat produced by the decomposition of plant material helped incubate them. Many mothers stayed close to the nest, defended the clutch from predators, and when the hatchlings emerged, guided them to the water or even carried them in their mouths. This parental care increased the survival chances of new generations, especially important in a period when ecosystems were still unstable and climate variations could ruin an entire season. The presence of crocodilians altered the dynamics of river ecosystems. As large predators, they controlled populations of fish, amphibians, and other aquatic vertebrates. When prey became too abundant, hunting pressure kept it in check. At the same time, the carcasses of animals that died of natural causes and were partially or fully consumed by crocodilians provided nutrients to the system. Bones, fragments of meat, and excrement enriched the bottoms of rivers and lagoons, fed invertebrate communities, and contributed to the recycling of organic matter. On the banks, the paths they created while dragging themselves, the shelters they dug, and the shores eroded by their weight created microhabitats for other species. Small mammals used cracks and abandoned burrows. Smaller amphibians and reptiles found refuge in cavities formed by roots and disturbed mud. Indirectly, these large predators acted as ecosystem engineers, altering the terrain and creating opportunities for other organisms. For mammals that were beginning to diversify, the presence of crocodilians imposed limits and challenges. Any species attempting to live near water faced the risk of becoming prey. Some mammals stayed deep in the forest, away from the banks. Others learned to cross rivers at shallower spots or at times of the day when crocodilian activity was reduced. Natural selection favored individuals who were more cautious, faster, or nocturnal, avoiding direct encounters with these predators. However, the relationship was not only one of threat. In many cases, the remains of animals hunted by crocodilians provided food for scavenger mammals, birds, and other vertebrates. River edges became places of risk, but also of abundance. For a small creature, sniffing around a sleeping crocodilian could mean the difference between hunger and accessing a feast of leftovers. Mammals, from small shadows to architects of the New World. For almost the entire late Cretaceous, most mammals lived in the background. They were small, in many cases nocturnal, and occupied narrow niches. Insectivores, discrete omnivores, some climbers, others diggers. While the large dinosaurs dominated the day and open spaces, these mammalian animals remained in burrows, low branches, and dark corners of the forest. Their real diversity was already significant, but most of their evolutionary experiments were limited by the presence of giants that controlled most of the biomass. When the impact occurred and mass extinction spread across the planet, this balance of power changed fundamentally. In a matter of hundreds of thousands of years, mammals stopped being merely secondary and began to diversify at an astonishing rate. Fossil records show that during the Paleocene, the number of species and variety of forms increased markedly with an explosion of new bodies, dentitions, and lifestyles. Current reconstructions indicate that after the initial crisis, mammal species richness multiplied, partly because the niches left by dinosaurs remained empty and partly because mammals already had prior evolutionary preparation. Many lineages had begun to diversify before the KPG boundary, although they could not fully expand. The collapse of large reptiles opened the door to ecological release, and mammals took advantage of this opportunity. During the Danian, most remained small. The typical scene of an early Paleocene forest did not yet show large ungulates or giant predators, but a network of creatures the size of mice, rats, squirrels, or small cats. Many had elongated bodies, agile legs, and prehensile or at least flexible tails. In the dim understory, these mammals sniffed through leaf litter, climbed young trunks, leapt among roots, and hid in burrows and tree cavities. Among them were the multituberculates, a group of mammals with teeth full of cusps resembling rodents, although they were not. These animals had survived the impact and entered the Paleocene with remarkable diversity. Some species lived in burrows, others moved through trees like squirrels, and others jumped like small running rodents. Their dentition allowed them to crush seeds, fruits, and tough vegetation, making them highly versatile herbivores and omnivores in Paleocene forests. At the same time, placental mammals, distant ancestors of most current species, began experimenting with new forms. Today, it is known that in the Paleocene several groups emerged or consolidated that would later give rise to modern orders. True insectivores, early relatives of carnivores, and especially the so-called archaic ungulates, traditionally known as condylarths. These latter were not yet horses, cows, or pigs, but already showed dentition and limbs adapted to walking and feeding on soft plants, leaves, and fruits. In sites in North and South America, remains of these early ungulates appear precisely in Paleocene sediments, including the Danian and the following interval. While some lineages leaned toward herbivorous diets, others specialized in carnivory. Small predators with sharp teeth and elongated skulls hunted insects, lizards, amphibians, and other mammals. Their fossil traces appear mostly in molariforms with sharp cusps and in skeletal adaptations for rapid movements. In a world where crocodilians dominated water and riverbanks, these carnivorous mammals found their niche mainly on the forest floor and among branches, chasing small prey, avoiding river dangers. Many Danian mammals were opportunistic omnivores. They mixed insects, fruits, seeds, and carrion in their diet. This dietary flexibility proved extremely useful in still unstable ecosystems, where fruit yields could vary greatly from year to year and where vegetation growth alternated with periods of climatic stress. Individuals capable of switching resources according to availability survived better and left more offspring, driving rapid evolution toward versatile dentitions and exploratory behaviors. In reproduction, many small mammals responded with high turnover strategies, large litters, short life cycles, fast growth. When an ecosystem was under reconstruction, this dynamic allowed populations to recover quickly after droughts, floods, or local fires. Although direct behavioral evidence is limited, patterns observed in their descendants and in the structure of fossil sites suggest intense reproductive cycles in several lineages, especially among insectivores and multituberculates. Ecological relationships also changed. In the absence of massive herbivorous dinosaurs, mammals gradually began occupying intermediate steps of trophic networks. At first, many concentrated in the lower forest strata and understory, but soon some lineages tried the path of intermediate life, not only on the ground, nor only in the trees, but combining both dimensions. This tendency toward three-dimensionality was crucial because it prepared the ground for the appearance of more specialized forms, such as clearly arboreal mammals of the Middle and Late Paleocene. Among them were the Plesiadapiforms, protagonists of the next chapter, and historical candidates as early relatives of primates. Mammals also began to take on roles now recognized as fundamental for ecosystems: seed dispersers, insect population controllers, soil engineers. By consuming fruits and defecating seeds away from the parent plant, they contributed to expanding young forests. By digging burrows, they aerated the soil and facilitated water infiltration. By feeding on large quantities of insects, they limited potential pests on recovering vegetation. Although these functions were understood much later, the Danian was already testing them in the form of small furry bodies running among wet leaves. Over time, the combination of warm climate, expanding forests, and empty niches drove true adaptive radiation. Mammals not only increased in species number, they also explored new body forms, from streamlined runners to robust climbers and incipient gliders in later times. The trajectory that would lead to horses, rhinoceroses, bats, whales, and primates began in this scenario of small vertebrates that, step by step, occupied every available corner of the Paleocene. Life in the trees, Plesiadapiforms, and the dawn of the primate lineage. When the Danian forests finished closing their canopy in many regions, Earth ceased to be just a landscape of rivers, ferns, and burned trunks. It became a vertical world. Branches, previously only occasional shelters, transformed into a continuous network of trunks, lianas, and overlapping crowns. There, in that third dimension of the forest, one of the most influential stories of the Cenozoic began discreetly. That of the mammals that made trees their home and that over time gave rise to the primate lineage. In the first millions of years after the extinction, small insectivorous and omnivorous mammals climbed young trunks, moved along thick branches, and used holes in the bark as shelters. Many still resembled shrews, primitive squirrels, or modern tree shrews. They had elongated snouts, lateral eyes, and furry tails. However, some lineages began to show subtle changes in teeth, ankles, and hands. These changes heralded the transition toward increasingly primate-like forms. Among the protagonists of this dawn was Purgatorius, a small mammal the size of a rat, whose remains appeared in the earliest Paleocene sediments just a few 100,000 years after the KPG boundary. For decades it was known only from teeth and jaw fragments, but recent studies of ankle bones showed that its joints allowed movements typical of animals that climbed and moved along branches. Purgatorius moved in a world where dinosaurs no longer dominated, and its arboreal lifestyle made it one of the earliest candidates for the title of proto-primate. These early mammals were part of a broader group known as Plesiadapiforms, a group of Paleocene and Eocene mammals that many researchers today consider close relatives, or even very basal members of the primate stem. The exact position of this group is still debated, but their anatomy provided clear clues. Dentitions adapted to mixed diets of fruits, seeds, and insects. Long tails that likely helped with balance, and, in later forms, hands and feet with a much greater grasping ability than other mammals of their time. In the Danian, the forest still did not resemble a modern tropical rainforest, but it already displayed multiple layers of vegetation and a growing diversity of flowering plants. Small fruits, fleshy seeds, and flower-associated insects provided a concentrated food source in the canopy. For a small mammal, climbing trees meant access to less exploited resources and, at the same time, a way to avoid many ground predators, including crocodilians lurking in rivers and swamps. The tree became both a supermarket and a refuge. As the Paleocene progressed, some lines of Plesiadapiforms specialized even more in arboreal life. In the fossil record, especially toward the end of the Paleocene, forms such as Carpolestis simpsoni appeared, a small mammal that already displayed a key feature, an opposable big toe with a nail instead of a claw capable of firmly grasping thin branches. At the same time, its hands retained claws, suggesting a gradual transition toward the set of traits typical of later primates. Although Carpolestis lived slightly after the Danian, its existence indicates the path that was already being prepared in those early forests. These animals did not yet have all the hallmarks of modern primates. Their eyes were not fully forward-facing, the brain had not yet reached the relative volume of a monkey or lemur, and their ankles were not specialized for long jumps. But precise branch grasping, a diet based on fruits and insects, and systematic use of the canopy were already part of their lifestyle. Studies of Plesiadapiform skeletons show a surprising diversity of postures and movements. Some moved slowly along large branches, others climbed nimbly, and still others likely ran and jumped between trunks. The relationship between these arboreal mammals and flowering plants was profound. As forests became denser and richer in angiosperms, opportunities increased for animals capable of locating ripe fruits, chewing pulp, and dispersing seeds. It has been proposed that coevolution between early primates and fruiting plants may have begun already in the Paleocene. Mammals fed on fruits and, moving from tree to tree, deposited seeds in new locations, helping forests expand and diversify. In return, plants that produced more visible, aromatic, or accessible fruits were favored by these dispersers. Day-to-day life in the trees was not easy. Branches offered food but also required balance and coordination. A fall from the canopy could be fatal. Individuals that developed more mobile ankles, more flexible fingers, and better grasping abilities had a higher chance of surviving, moving without falling, and reaching resources in time. Generation after generation, these anatomical advantages accumulated. What began as an insectivorous climbing mammal slowly transformed into an animal for which the three-dimensional forest was its natural habitat. Meanwhile, the rest of the world continued to change. Crocodilians still dominated rivers. Archaic ungulates explored forest clearings and more open areas. Small carnivorous mammals stalked among the undergrowth. But in the canopy, Plesiodapiforms and other early euarchonts occupied a relatively protected niche where direct competition with those groups was lower. This certain vertical autonomy allowed them to follow their own evolutionary path. From today's perspective, the Danian is seen as the prologue to this story. Forests that arose after the extinction provided the basic structure. The warm and humid climate maintained the necessary productivity. Small mammals provided constant experimentation with new ways of life. From this combination arose the possibility of a lineage that, millions of years later, would include lemurs, monkeys, apes, and ultimately humans. From the Paleocene to the Eocene, warmings, migrations, and new rules. As the Danian receded and the Paleocene advanced, the planet did not return to the state it had been in before the extinction, but continued to change. The millions of years following the impact led Earth toward an even warmer, wetter, and biologically more dynamic world. The planet under reconstruction of the early Paleocene transformed into a complex setting where mammals, birds, and aquatic reptiles were already competing, migrating, and adapting under an increasingly extreme heat-oriented climate. During the Middle and Late Paleocene, the carbon dioxide remaining in the atmosphere, combined with new volcanic emissions and feedbacks from the climate system itself, maintained a strong greenhouse effect. The poles retained very small or non-existent ice caps, and warm seas bathed extensive continental shelves. Average temperatures, which had fallen after the extinction, rose again, and in many regions even exceeded those of the late Cretaceous. Against this backdrop, one of the most intense warming episodes of the Cenozoic era was prepared, the Paleocene-Eocene thermal maximum, which occurred around 56 million years ago. Before that peak, the Paleocene itself was already showing its transition. Forests that the Danian had established as young structures became denser and more diverse. At high latitudes, where conifers and tundra dominate today, mixed forests and wooded swamps grew. In interior basins, wide rivers meandered through humid jungles and plains covered in lush vegetation. Crocodilians, turtles, and other warm-climate reptiles inhabited regions that today would seem too cold for them, evidence that the entire planet operated under different thermal rules. On land, mammals underwent a qualitative leap. What had been small, inconspicuous bodies in the Danian began transforming into faunas with increasingly larger and more specialized species. Archaic ungulates increased in size, developed limbs better adapted for walking and running, and dentitions more suited to processing leaves, shoots, and fruits. On some continents, mammals appeared that already rivaled the medium-bodied herbivorous dinosaurs of the past in body mass, although they still did not reach the giants of the Mesozoic. At the same time, more powerful mammalian predators emerged. Groups such as the creodonts, distant relatives of modern carnivores, evolved toward forms with robust skulls, long canines, and bodies built to chase and take down large prey. On the forest floor, in clearings and along river margins, these hunters occupied the role once held by theropods, but with different strategies. More group chases, greater reliance on smell, more dependence on agility than sheer mass. Arboreal mammals continued their own story. Increasingly specialized plesiadapiforms and later the first true early Eocene primates took advantage of dense forests to deploy a whole range of movements and diets. Some developed longer leaps between branches, others strengthened their grip with fingers and nails, and many expanded their dependence on fruits, flowers, and small invertebrates. In the treetops, evolutionary radiation continued almost independently of what was happening on the ground. Meanwhile, the continental map allowed something that had been different in the time of the dinosaurs: large mammal migrations across land bridges at high latitudes. The warm climate allowed forests and favorable habitats to spread across regions connecting North America with Eurasia, either through the North Atlantic or via Beringia. These vegetated corridors provided routes through which groups of mammals could cross from one continent to another. Lineages that evolved in one area appeared, millions of years later, in another, carrying new combinations of traits with them. When the Paleocene came to an end and the Eocene began, the climate system became even more destabilized. Some mechanism triggered the Paleocene-Eocene thermal maximum. Global temperatures rose several degrees in a geologically brief interval. Oceans warmed, became more acidic, and marine faunas responded with changes in species distributions and community composition. On land, tropical forests expanded into temperate latitudes, and mammals adapted to heat and humidity invaded regions that had previously been cooler. This warming episode further accelerated migrations and adaptive radiations. Within a few million years, new families of mammals dispersed across Eurasia, North America, and other continental masses. Some primate lineages, for example, appeared almost simultaneously in different regions of the Northern Hemisphere, suggesting that they moved rapidly through forested corridors before the climate changed again. The same happened with certain groups of ungulates and early carnivores. The new ecological rules of the early Eocene were now completely distinct from the Mesozoic world. On land, dinosaurs were only fossils. The dominant giants were now herbivorous mammals, with mammalian predators and birds of prey at the top tiers. Birds also occupied niches previously held by pterosaurs, including large, flightless forms that acted as super-predators in some ecosystems. In rivers and swamps, crocodilians maintained their role as principal hunters but coexisted with mammals increasingly confident in approaching water, some of them already adapted to swimming and a semi-aquatic life. In the seas, the change manifested in a different way. As the climate warmed and coastal ecosystems became more productive, certain ungulate-like terrestrial mammals began exploring coastlines, brackish marshes, and shallow waters more frequently. They sought aquatic plants, crustaceans, mollusks, and small fish. At first, they swam just enough to feed, but generation after generation, some lineages evolved limbs better adapted for propulsion in water, stronger tails, and more elongated bodies. Towards the sea, the path that will lead to cetaceans. When the Paleocene progressed and the Eocene began, the coasts of many continents ceased to be mere transitional lines between forest and ocean. They became zones of opportunity. Warm bays, sediment-laden estuaries, and shallow seas surrounded large continental shelves. There, the mixture of fresh and salt water concentrated nutrients, schools of fish, mollusks, crustaceans, and aquatic plants. In that environment, certain terrestrial mammals began to view the sea not only as a boundary but as a source of food. On solid land, archaic ungulates had already diversified. Many of them had relatively long legs, medium-sized bodies, and dentition adapted to leaves, shoots, and fruits. However, some lineages showed another trend. They began to explore wet areas, marshes, and muddy shores. These animals walked among the roots of primitive mangroves, waded in shallow waters, and fed on soft vegetation growing in saturated soils. From a behavioral perspective, the next step, entering the water slightly to reach more food, was small. Today, it is known that the ancestors of cetaceans belonged to a group of artiodactyl mammals, distant relatives of modern hippos and other even-toed ungulates. These animals had robust bodies, legs capable of supporting their weight on land, but also allowing them to move freely on soft substrates. They started as mammals that only approached water to drink or cool off, and eventually began using shores as regular feeding zones. Generation after generation, some individuals spent more time in water than out of it. The advantages of this behavior were clear. In estuaries and warm bays, competition with other terrestrial mammals was lower. The large dinosaurs were gone, and crocodilians, though dangerous, were concentrated in rivers and specific areas. A sufficiently large mammal, capable of swimming with some skill, could exploit schools of fish and crustaceans with fewer rivals. Moreover, water provided partial refuge from terrestrial predators. It was enough to venture a few meters further to make hunting more difficult for carnivores not adapted to swimming. This behavioral shift began to be reflected in anatomy. The first semi-aquatic mammals developed stronger hind limbs to propel themselves in water, more muscular tails, and longer, more flexible bodies. When submerged, they moved their hind limbs up and down, combining a locomotion style still reminiscent of an ungulate with the first sketches of more efficient swimming. On land, they continued to walk, albeit perhaps less elegantly than their fully terrestrial relatives. In water, however, they gained an advantage. Over time, some of these lineages gave rise to forms like Pachycetus, which lived in the early Eocene. This animal still looked like a terrestrial mammal with sturdy legs and a body supported on the ground, but its skull displayed features of the inner ear that foreshadowed adaptations for hearing in aquatic environments. Pachycetus probably hunted along the shores and in very shallow waters, alternating slow steps on sediments with brief dives in search of fish and other organisms. In essence, it was a mammal dividing its life between land and the water's edge. In later stages, other descendants of these lineages, such as Ambulocetus, took the transition further. These animals, fully part of the Eocene, resembled a mix between a crocodile and a mammal: robust legs, long torso, powerful tail, and elongated snout. They walked awkwardly on land but swam powerfully, mainly propelling themselves with their hind legs and undulating their bodies. Ambulocetus may have launched into the water from the shores to ambush prey, not unlike how modern crocodilians attack animals approaching to drink. Although these proper names correspond to times slightly after the Danian, their history cannot be understood without the world the Paleocene had created. Warm coasts, abundant food in shallow waters, and the absence of giant marine reptiles like mosasaurs, which had disappeared during the extinction, created an ocean full of empty niches. Where predatory reptiles once swam, there were now only large fish, sharks, and a few rays. For a mammal willing to change its way of life, the sea offered ample space. The transition was neither uniform nor linear. Many mammals that tried the water likely failed and went extinct. Others were trapped in life forms too intermediate, without sufficient adaptations for either sea or land. But a few lineages moved forward. Their legs gradually transformed into flippers, their bodies became more hydrodynamic, and their spines gained flexibility, allowing them to swim with vertical tail undulations. The skull also changed. The nostrils shifted to the upper part of the snout on the way to the dorsal position now occupied by the blowholes of whales and dolphins. Hearing adapted to water. The middle ear bones modified to better transmit aquatic vibrations. The skull developed structures that insulated sound and allowed prey to be located through echoes and subtle signals. In the dimness of turbid waters, sight was no longer enough. Precise hearing became a vital tool. The changes that were just beginning in Pachycetus were consolidated in later forms, ultimately creating the sophisticated auditory system of modern cetaceans. In parallel, reproduction accompanied the transition. The first basal cetaceans still gave birth on land or in very shallow waters, where they could support their young with the help of the bottom. However, as bodies became more aquatic and legs transformed into flippers, returning to land became increasingly difficult. There came a point when giving birth in water was the only viable option. The young were born already adapted to swimming from the first moment, breathed air at the surface, and stayed close to their mothers, feeding on fat-rich milk. This maternal bond, typical of mammals, remained even as everything else changed. At the end of this process, the ocean hosted something the Mesozoic had not known. Fully marine mammals, capable of covering long distances, diving deep, communicating through complex sounds, and exploiting resources from microscopic plankton to large fish. Filter-feeding whales and predatory odontocetes would arrive later in advanced stages of the Eocene and Oligocene, but their roots lay in those ungulate mammals who, in a world shaped by the extinction of dinosaurs, chose a different path. Thus, the story that began with small mammals hiding in the shadows of the Cretaceous ended by leading some of their descendants back to the sea. The Danian had seen crocodilians become rulers of rivers and young forests provide refuge for the first primates. With the transition from the Paleocene to the Eocene, part of that same mammalian lineage left the safety of the forest and ventured into the oceanic vastness, inaugurating a new form of dominion. The giants of the sea, distant heirs of terrestrial creatures who, after the fall of the dinosaurs, found their ultimate future in the waves.